So thank you and welcome everybody to today's C2 Smart webinar. I am Lizzie, the Research Project Manager at C2 Smart, which is a US DOT Tier 1 University Transportation Research Center. And C2 Smart leverages recent advances in big data and technology to solve today's urban mobility challenges. Today's webinar is one-to-many simulator interface with virtual testbed for equitable tech transfer, which is a project conducted in collaboration between NYU and the University of Washington. Our presenter is Hai Yang, who is starting his third year as a PhD candidate at NYU and whose field of study is urban logistics analysis. Hai received his undergraduate degree from the Chinese University of Hong Kong and his master's from Northwestern University. And then from the University of Washington, we have Jeff Ban, a William M. and Marilyn M. Connor Endowed Professor in UW's Civil and Environmental Engineering School. And then just some quick notes before we get started. We'll be recording this session and then uploading it to C2 Smart YouTube channel. And we encourage everybody to participate today by asking questions. And you can do so by pressing the Q&A button at the bottom of your Zoom window. And then we'll read out the questions at the end of the presentation. And with that, I will hand things over to Hai to get us started.
Okay, thank you, Liz. Hello, everybody, I'm Hai Yang. I will share my screen now. So can everybody here see my screen?
Yep, looks great.
Okay, cool. So thank you for participating. I'm Hai Yang, and this is the project. Our project is one-to-many simulator interface with virtual testbed for equitable tech transfer. The project lead is Professor Joseph Chow, and the co-lead are Professor Con Osbey and Professor Jeff Ban. Several students are involved in this project, including one undergraduate student during last year's summer program. And we are grateful to have all the participants into these projects. So here is the table of content. So it will break down into majorly 4 parts, excluding the background and summary. It will be the general project objective, and the overall API structure, and some very detailed API design, which we will be focusing on the NYU team part. This is a collaborative project between NYU team and the UW team, but for this webinar, we will focusing on the NYU team part. And some experiments and evaluation based on these developed tools and a brief summary. So just a quick recap of the background. This project is focusing on the simulation tools. So the simulation is a very essential tool in the transportation study. And throughout decades of this study, numerous simulation tools have been developed. And they are for different kinds of transportation studies and analysis. So for example, there are MATSim, there are Sumo. Sumo is mainly focusing on the traffic analysis. There are MovieSum, there are Transims. I believe this is mainly focusing on the regional transit, and there are VCM, and countless of them. So there are many of them. They can address different kinds of transportation studies, but they are very hard to incorporate. So it's kind of hard to pull different kinds of simulation tools together and let them to run collaboratively and to have a very integrated result. So that's a pretty big problem. And one solution to do that was to use a core multi-agent simulation, for example, the MATSim tool, and then develop different kinds of extensions to extend. So basically, the added modules to the multi-agent simulation, and to expand its capabilities of simulating the transportation system further and further. So, like shown in this figure, so there may be some existing simulators for a very specific transportation system or a very specific traffic control plan. So if we want to integrate that into a core multi-agent simulator, we will need to translate those simulators into individual extensions, and then add those extensions into the core multi-agent simulator, and then run the whole simulator for integrated results. For example, there could be some trip agenda with these complex transportation system, or different links of the vehicle performance. And if we want to focusing on the traffic side, we'll evaluate the traffic volume, the vehicle trajectories, etc. So this is a common way to tackle the expanding scenarios of novel transportation studies and services. But there are some shortcomings for using this kind of system. One is it has some limitations on the extension. For example, the MATSim, because MATSim is using a more mesoscopic traffic simulation, so it cannot really handle a more microscopic traffic control algorithms into its traffic simulation part. So if we really want to implement some like very novel traffic control plan into the MATSim simulation, it's not really possible to use an extension to do that. So that is one shortcoming. And another one is because it's an added module to the existing multi-agent simulator. So it's kind of hard to convert the algorithm into an extension that really has the same underlying design as the multi-agent simulator, because they need to be aligned and the logic need to be assigned together. So the developer needs to have very strong fundamental knowledge of the simulator, the multi-agent simulator, for example, MATSim itself, and then the language need to be using this. We need to use the same language to write the module. So for MATSim, it's Java. But if the scholar or a developer is not very efficient in Java, then he or she will have a very hard time to convert things into a MATSim module. So to tackle that, this is the objective of this project, is to develop a platform or API. So essentially use that API or platform as a third party to connect the two parts, which are the multi-agent simulator with different kinds of external simulators. So these simulators could be written in different kinds of language, for example, Python or C++, not essentially need to be Java in this case if we're using MATSim as the core multi-agent simulator. So we will use this API to connect the two parts to translate different information using the API and feed them back to the corresponding parts. So in this way, we will make an integrated outcome by combining these simulators in this way that, so we don't need to really convert anything for the simulators to convert those simulators into added modules or extensions. You will save a lot of work and you will make, so with the developers, you will have the freedom to develop their own local simulator in their own language, whatever language they are comfortable with, and then use this API to connect those simulators with the MATSim. So for the NYU team, we are focusing on the ride pooling simulator to connect it with the MATSim. And for the UW team, they are more focusing on the traffic side. So they are integrating the MATSim with Sumo, which is a dedicated traffic simulator. And to use these kind of APIs, we can actually apply different added services or traffic control plans in the overall MATSim system. So this scenario illustrated in this figure has like 3 added services into the whole New York City. So if we're running a whole New York City as our transportation system, we can define different subregions, so a local area, to apply different novel services, no matter it's ride pooling service or other kind of service. And also we can apply a local level control plan, for example, the signal control into certain areas or intersections, and to see how these local applications will have the effect on the overall network of the whole New York City. So I will briefly introduce some of the general structure of those APIs, and then I will break it down further, especially for the NYU part, the ride pooling focused API, how the general flow and the basic logic behind the overall API design. So essentially, we are actually like generating, so we will have some predetermined assumptions in the MATSim. I will let it run, but after getting the initial MATSim results, we'll extract the trip lags that we want to focus on, and then feed those extracted trip information into the external simulator, and to let it run again, and to have a more realized result, and replace that result into the previously extracted trips. So that's the core concept of this kind of API structure, as illustrated in the figure here. So for a specific agent, we're using a specific agent as an example. So for a specific agent, if his trip plan is to going from home to work, and then to have a meal, and then after the meal he will go back home. And for the trip lag between the work to restaurants, if one of the options of him is to use a ride pooling service, and he will have, so in the initial MATSim run, we will give some predetermined travel speed to this kind of trip service. It's a very generalized parameter. So he will use this information to have a perceived trip time. In this example, it's 15 minutes, but it's not a realized one. By fetching this specific part of the trip lag into and feed it into the external simulator, in our case, it's a ride pooling simulator, and then the result will be the realized trip time for this specific trip lag. So in the figure here, the realized trip time is 12 minutes. So this realized trip information will substitute the previously 15-minute trip time, and then this trip agenda for this specific agent will be is updated with more realized usage of a ride pooling service. For the traffic side, which is the UW team's work, it's kind of like it's a very similar idea. So there will be the parts, like the local parts, using the MATSim, using the Sumo simulator to have a more complex road network conditions, and maybe some more specific traffic control plans applied to that area. So the arrival time into the Sumo area will be generated from MATSim, and the actual travel time inside the Sumo area will be simulated using the Sumo simulator, and then that trip time will be, and the arrival time of the another part, like the outside part of the MATSim area, will be updated so that it can reflect a realized travel time inside the focused study area. So that's how the general it's by the application and the realization of this algorithm is much more complex, but the general idea of that is as simple as it is. So to really dive into like so this is a very high level generalized idea of how this API could work. But we will dive further into a really detailed algorithm, the workflow of how the ride pooling simulator, so that's the NYU team's work, to have a better look of how this kind of trip extraction and update and the feedback into the original trip agenda, how this kind of process work. We'll have a deeper look into it. So this is like a further breakdown of the previously mentioned ride pooling simulator related API. It is called the FD platform, which is named as the Fleet Demand Platform. So that's the name of the API that the NYU team has developed. So we are using ride pooling simulator as a studied focus, but in future applications, it can be modified to accommodate different kinds of fleet-based simulators. For example, it can be fixed route transit simulator or other kinds of fleet-based simulators that use a fleet to provide certain transportation services. So the general idea is to run the MATSim first. So we will have the initial setting of the configuration file and the trip plan file. That's for the initial running of the MATSim itself. And then we will have a realized trip itinerary based on the MATSim run. But the MATSim run, in this case, the initial trip plan and the configuration file, they have some predetermined estimation of those focused ride pooling service in our case. Those are the estimation, but we want to update with a more realized information by running through the ride pooling simulator. So when we get the initial estimation of the trip itinerary, which contains all the details of the trips that each agent participates, then we will extract the ride pooling trips in our example, because we are focusing on the ride pooling simulator. So we will extract the ride pooling trips from the trip itinerary to get all the information needed to create a request log. So it will be a list of all the trips that requesting the ride pooling service and submit that into the ride pooling simulator, combined with other needed documents, which will be explained in the following slides. And then after running this ride pooling simulator, we will have a more realized trip records, which are actually how reflecting the real world scenario of using these kind of ride pooling services with the realized trip itinerary. And so we will replace that, we will replace the original trip lag by this new updated information. So by combining these two parts, we will have an updated trip itinerary. But only running once is not enough, because of the simulation itself. We need multiple cycles to make sure that it will reach like a more stabilized state. And so by only running it, because the initial estimate, initial trip plan is just a pure guess of how the ride pooling will be, how many ride pooling trips there will be, but it may not be realized, like it may not really reflect the real world scenario of all the agents, considering like the trip time, the realized trip time, and the actual cost of the ride pooling services. So in order to get to that stabilized status, we need to check some conditions to make sure that it reaches the level we want it to be. And if the stopping condition or the stopping criteria has not met, we will use the updated trip itinerary as the next round of initial trip plan, and then feed it back to the MATSim again. And these information will be also reflected in the configuration file, which I will explain in the following steps. And then these cycles, we will call it the FD platform cycle. After several cycles, we will meet a certain stopping condition. And when the stopping condition is met, we will use this updated trip itinerary as the final result, which can be further analyzed by extracting different kinds of information, trip information, or the agents and the vehicles associated to those trips to do all kinds of analysis in the following steps. So here are some further breakdown of how like each steps work. So for the initial trip plan and the configuration file, as we mentioned, we need to have some initial assignment of those novel, like it could be existing or non-existing trip modes. But in here, we are using the DRT as to represent the right pooling service in this demonstration. It's just a quick illustration of how the different kinds of files would be with the specific elements we want to specify. So in here, we are defining the DRT as the right pooling service. We use this to represent the right pooling trips. And in here, because in the MATSim, we don't really have a mechanism to accurately simulate the right pooling service in our case. So we will define the right pooling service as a teleportation mode. So essentially, it will not be actually running on the road. It will just popping from one point to another point with the defined time, and with using the straight line connecting these 2 points. So it's approximation of how the general trip, how long you could take by adjusting the teleportation speed. So every single run of MATSim will adjust these teleportation mode speed, so which defines how fast the teleportation speed will be for these right pooling service, to have a general idea of how fast it could be in the MATSim run. So the teleportation speed, if we're running at the very beginning, we'll have a very a quick estimation, or based on other modes, or we'll have some initial estimation, like how fast in general these kind of service would be. For example, we can use the taxi to have an aggregated average speed of taxi trips, to use that as an initial estimation or initial guess of this kind of service, but it will update accordingly in the following cycles. Also, we need to define the parameters for these specific modes, because the parameters will be used to update the scoring of each for each agent. So the MATSim can really decide what kind of modes, or how the agents will choose different kinds of modes in a more rational way. So we need to have some. Also, we need to have some initial estimation of how different values, like score values, will be assigned to this specific mode, which can be estimated using some existing travel modes, for example, taxi, or if there's other like on-demand services provided in the system. And after that, we will feed this information into MATSim. But because we want to have some generate enough set of perceived travel plan to let the agent to select which one will be the best for them. So you will have sufficient mode changes for each MATSim run. So it will be we want to make each MATSim run to be to have some fluctuation of the mode changes. So there will be so the system can keep updating the novel the modes we want to focus on. In the setting, we want to run multiple days of MATSim in one MATSim run. So because here is the mechanism of MATSim itself, so it will have as a trip plan feeding and have the score generated, and then if we run in multiple days, you will generate multiple days of different kinds of perceived travel plans, and the plan with the highest score will be selected in the final round, and then that final trip plan will be the final trip itinerary for the following steps. So this is a quick snapshot of the trip itinerary after running the initial MATSim run. So in here, for the DRT service, which stands for the right pooling service in our case, the routes is showing as generic, because we are using teleportation and as the mode. So it will be a generic route type. without any route detail because it's just teleporting from one point to another. But you will have a travel time because we have the B-line distance, which is the Euclidean distance between the 2 points, and use that and use the previously determined travel speed to generate an estimation of the travel time these trip could take. So that will be the case for the following trip as well. And because this is just a pure initial estimation of the ride pooling service, we need to update it. In order to update that, we need to feed those information into the following ride pooling simulator. In this case, we need to pull out the essential information, for example, the person ID, the trip ID, the trip start and end coordinates, and the trip start time to help to generate a request log for the local simulator. And in this case, we need to have a check because most of the in our case, the ride pooling simulator is not a citywide service. It will be confined in a specific region, and then that's some of the a common practice in the real world. So some initial generated trip plans by you, or like they are perceiving to use the ride pooling service, those trips may fall out of the region, so they may not be feasible to actually be used as a ride pooling service. So in this case, like as illustrated here, if the square is service region and the trip one, there are two trip one and trip two, but you can see trip one end of the trip is actually falling out of the region, so we will perceive it as an ineligible trip. In that case, that trip will be switched to other modes. So in the current version, it's deterministically to the public transit, but in the following development, we can engage another layer of mode choice model to choose what other modes can be chosen. But in the current version, we are switching it to public transit in this case. So for this example, the trip one will be switched to public transit, but the trip two will be extracted to the request log. So the trip two will be updated accordingly in the following local simulator. So for the ride pooling simulator itself, we need to have multiple files to let it run. So we need the request file, which will be generated by extracting the information from the previously generated trip itinerary. And we need to define the subnetwork file, which defines the service area that I briefly mentioned here. So if that service will be provided in a specific region, and the stops, so some services we can define as a door-to-door service, and some of them will be more like a stop-based service. So we also, if there are stops involved, we need to also include the stops in the subnetwork file. And the operational parameters, which will define how this ride pooling simulator can work. For example, how many vehicles are in one fleet, and what the size of the vehicle, and what actual strategy a fleet is using to provide the ride pooling service. So after inputting these into the ride pooling simulator, we will have an output of the realized ride pooling trip records. So which can be shown here, which is demonstrated here. So we will have the traveler ID and the trip start time. The trip start time will keep the same because they are the original time that they want to depart. But the trip end time actually changes. So the travel time will be adjusted accordingly. So compared to the previous one, the first trip here, it used to be 9 minutes, but here by running through the simulator, the actual realized time is actually faster. It's 5 minutes. So these trip time will be replaced, and the same case for the following trip leg as well. So in this case, we actually reflect the realized travel time into the trip itinerary generated by the MATSim. And this itinerary can actually be used as an input in the following MATSim to run again. So that's how it can be fed back as a cycle to going through this cycle again and again to generate the consecutive runs and to generate consecutive output. And one thing I need to mention is some of the trips, if there are some like very restricted limitation on the right pooling resources, for example, some of the trips may be rejected by the provider because there are limited number of vehicles running on the road. So it could be possible that some of the trips are rejected. So if those trips are rejected, those trips, they supposedly could use ride pooling service, but because they were actually rejected, they will be switched to other modes. And in our case, it will be switched to the public transit again. So, for example, in this case, for example, for the second trip leg of this agent, if his or her trip is rejected, the whole trip will be replaced by the public transit. So it will not be an updated time for this DRT trip. It will be a public transit in the consecutive run in the MATSim. And for the stopping criteria, because we need to determine when this cycle will stop and have a final output, the stopping criteria can vary by different scenarios. But in our case, a general scenario would be to see through the overall use of the number of trips actually using that specific service, and to see whether that trip number fluctuates to a certain point that it kind of stabilized. So for example, we can use a 5-cycle moving average. Which means that after running 5 cycles of FD platform cycles, we can calculate in each cycle the final outcome, how many trips are actually using a specific ride pooling service. And if the number or the percentage of that number compared to the overall trips kind of stabilize to a threshold, we'll stop it. And we'll use the latest trip itinerary as the final outcome. So that's how the overall, so I can go back to this. So that's that's a kind of a detailed breakdown of how this overall system will work. And I hope it's clear enough. If you have any question, it can be answered by the end of this webinar. And then after explaining this, I will show some like examples of using this kind of application and how different scenarios can be evaluated using this tool. So first, we need to prove that the result of it is actually reliable. So there's an in the current development, we are incorporating one specific ride pooling simulator that's actually developed by the Build Lab, which is led by Professor Joseph Chow. And it's a collaborative result with the Volkswagen, the MOA team, which is a ride pooling service providers in Germany, in Hamburg specifically. So these are some of the parameters can be set to define a ride pooling service. And in here, we will set up some basic ride pooling service setting. So in the current version, in the current test cases, we are only defining one specific region, which is mostly the lower and middle Manhattan, and we define two ride pooling fleets that actually provide the ride pooling service, but they are using the same simulator with different parameter settings, so they will reflect different kinds of service strategies. And this is the region and the stop. So it's stop based. So these are all the stops. They are basically the intersections inside the whole network, inside the region. And the two fleets are named as DRT1 and DRT2. Each fleet has 9 vehicles, and each vehicle has 6 people capacity. And this is the basic setting of the two fleets and the service region. in order to really validate that to prove that the developed tool is reliable, it's actually reflecting the scenario of integrating the service into the overall system. We have a quick comparison between using the FD platform and the DRT extension. So in the current MATSim environment, there's a module called DRT, which stands for Demand Responsive Transport. So that DRT extension has some capabilities of simulating a ride pooling service in the system. So in this case, we can set the parameters to reflect to match it to in the FD platform to match what the DRT module can be done. So by matching these conditions, we can have a similar identical setting for the ride pooling services defined in the MATSim system. So I'm by running them in parallel and compare the final output, we can decide whether, and if the results are close, we can determine that the FD platform, the result is actually reliable because the DRT extension is like a more integrated way of like an added module or extension in the MATSim itself. So the scenario we are using, it's the initial trip plan, so which is also the population file. It's a subset of the MATSim-NYC work done in 2021, which is also done by the Build Lab led by Professor Joseph Chow. And we extract some of the agents and the trip plans inside the file. So it's a subset of it. It will make the system run quicker, but still relatively realistic environment. So it has around 5,000 agents and 932 trips in the whole trip plan. It's actually, we determined them as ride pooling trips. So those are actually originally defined as taxi trip, but we converted them to the ride pooling trips. So for the stopping criteria, we're using the 5-cycle average of ride pooling trip legs. That number of them have less than 1% fluctuation. So the 5-cycle average of the trip percentage among the whole trips will fluctuate less than 1% in these cycles. So we'll use that as a stopping criteria. So after running this, we find that the 50 runs of FD platform will be sufficient. So we match that number to the DRT extension MATSim run to have the comparison. So in the final results, so here is the progression of the number of trips or the ride pooling trip, defined ride pooling trips in the whole system by comparing the two products. And the final result is about 2% difference was like observed in terms of the number of ride pooling trips. But if we compare to the overall trip time, the aggregated trip time of ride pooling service, the gap is much closer. So it's around 1%. So we believe that this result is close enough to actually replicate using the FD platform outcome is a close replicate of the DRT extension. So we believe that the FD platform using the mechanism can actually produce a pretty integrated results with the MATSim. After determining that, we want to see how these kind of product can be used to evaluate some different kinds of scenarios that the DRT extension cannot actually do. So in here, as a quick mention, just a quick mention of the parameters can be defined in the ride pooling simulator we are using. There's one parameter called theta, which can determine the objective function of how the overall system cost or the system time can be minimized. So by setting theta to be 1, the objective function only minimizes the vehicle travel time. But when the theta is less than 1, the system will actually consider the passenger wait time into account. So when we set the theta less than 1, from the passenger side, they will experience less wait time for the vehicle coming. So from their perspective, the service would appear to be faster in the sense. So if we set theta to be 0.5 and another service, the theta to be 1, the theta of 0.5, the service using theta with 0.5 is actually will provide generally 30% faster, like a shorter travel time compared to using theta of 1. So in this case, we can really differentiate two different services among the two between the two fleets. That's what we did. So we defined that a flat cost will be imposed by both using DRT1 and DRT2, which are the two fleets providing the ride pooling service. We determined we want to see how the price, the cost change will actually affect the overall decision of the travel makers. So we defined that DRT1 charges 20% higher than the DRT2, so that's the flat cost difference. But and we create 3 different scenarios to see how the service speed will actually determine people's choice of their mode. So in scenario 1, both fleets both fleets are providing fast service. So they are set the theta to be 0.5. In the second scenario, they are both providing slower service. And the third scenario is one is providing faster service and one is providing slower service. And the result actually reflects what we expected, that using the FD platform, these are the results from the FD platform. So using the FD platform, different results the result can actually reflect these kind of heterogeneous the service settings. When both services are providing faster service, they are actually 25% high usage of a quicker service, even though if they are both quick, 25% more people will use a cheaper service. But even though they are facing more expensive service, people tend to use a faster service if they can. So that will be the third scenario. So, but when both services are kind of slow, the price difference will not really change much. So people tend to not using that service specifically. So the gap is like really close to nearly none. And so there's some quick analysis of results of using these kind of service, the FD platform, to see how the heterogeneous service setting can be reflected. We're also kind of interested in how it can be used for the equity study. So to see how like different kind of service setting can impact higher income group and lower income group. So it's more a social welfare study. So we have some further setting of like dividing the whole population. We chose a larger population file, so a larger trip plan, and divide them into 2 parts. One part of the population, they are not low income, which is a higher income group, and another part is a lower income group with a different value of time, so they can reflect how their perception of the value of travel. And we use an inequity score defined in Carsu and Morton paper to kind of it's kind of like a Gini value. So to calculate how inequitable the whole system is. So higher the value, the less equality they are existing inside the whole population. And then we run it in different scenarios, like a cheaper service but the faster speed, expensive service but a slow speed, and to see how it can be reflected in the overall equity in the whole population. After running it, we see that in the general case, like for the general public, no matter whether they will choose or not to choose the ride pooling service, the equity impact of this service changes is not that significant because it's only a subset, a very small amount, relatively small amount of people actually using this kind of service. So the service setting change will not actually really impact the general public. But if we're focusing on the actual passengers using those kind of service, we will observe that even though it could be cheaper, it could be faster. So in this case, the cheaper and the faster one, remember, higher the score, the less inequality. So when there's a very optimal service, like fast service but cheap service, it will actually increase the level of inequity. Why is that? Because in our population file, there are many more people actually in the higher income group. So the benefit will be lean towards them. So if there's a better service, everybody will use it, but the bigger group will benefit more. So that's why it's happening. So it's really important so this kind of implies that we need to apply some like better service into a less advantaged communities. For example, there are large group of people inside the income group value, low income groups, so they can benefit more by this kind of better services. But even though the impact, they are not like equal, but in the pure value of their own like benefits, if we break them down into the absolute value that they gain by using different kinds of service, so in this case, it's higher the score, the better the gain they are. So actually, everybody benefited by a better service. A faster service with a low charge will actually make everybody happy in this case, which is expected. So it is essential. So at least from this very quick analysis, we can see that the better service provided will benefit everybody, but it's better to apply it in a lower income community to make the impact, to make a better impact on the lower income groups. So just a quick mention. So that's something we've done regarding to the ride pooling simulator part. But we also want to have a quick mention of the part that the University of Washington team has been done. So they are actually developed a tool called VTD, that's which stands for Vehicle Traffic Demand Simulator. So it's focusing on the traffic side. So it incorporates the two traffic simulator, which are Unity and Sumo, and incorporate with the MATSim simulator. So because as previously mentioned, the MATSim cannot really handle a very microscopic traffic control plan. But by using this tool, we can actually apply some really advanced traffic control plan into the MATSim system and to see how it can change the overall traffic pattern for the whole network. So they have the UW team has done some applications based on these tools. So they've done some analysis by applying some advanced traffic signal control system on the intersection level and to see how this traffic signal plan can have a positive effect on a greater part inside the whole traffic network. And they also used the VTD simulator to generate the idea, to try to generate a city level result of the Seattle metropolitan area, and use that result to generate which is called the macroscopic fundamental diagrams based parameter control plan. And which can be fed back to the VTD simulator to actually evaluate how this kind of more advanced plan can impact the overall traffic pattern or the macroscopic traffic results in the whole city level. So that's the some quick mention of the VTD simulator. And yeah, so that's all about these two APIs, especially the ride pooling related API. So the FT platform, which focus on the ride pooling simulator integration with MATSim. The VTD simulator is focusing on the Sumo and Unity, which are the traffic simulators integration with MATSim. So by using these kind of tool, we're hoping that we will enable a future study of using this tool to evaluate a more complex transportation system without need to really develop really restricted formula for the extension of MATSim. Instead, we can have different development of local simulators with different kind of languages and integrated by using these applications in future. Yeah, yeah, that's all about the this project, and thank you for listening.
Thank you, Hai. And as a reminder, we invite all questions. So if anybody has one, please enter it now. And again, you do so by pressing the Q&A button at the bottom of your Zoom window.
Okay.
You can just give it a minute. All right, well, feel free to keep entering if you are, but otherwise, thank you everybody for joining today, and to Hai and Professor Ban for presenting at today's webinar. A recording will be made available on the center's YouTube channel and website. And again, this webinar was brought to you by C2 Smart and USDOT's University Transportation Center program. It looks like we don't have any questions, so thank you everybody and have a great weekend.
Thank you.
Thank you. Thank you. Hi. Bye-bye.